Hello everyone, today I am here to give a presentation of stress strain relationship, critical strain and irreversible strain of IBAD MOCVD based 2G STS wire under uniaxial tension. Myself, I am G. Sainath Reddy, bearing a pin number of 21955A 2109. And my topic is stress strain relationship, critical strain and irreversible strain of given wire. Abstract of this presentation. The mechanical behavior of RABCO coated conductor wire under uniaxial tension is largely determined by the two thickest components layer in the architecture, namely the substrate and the stabilizer. A rather complicated stress-strain relationship is often observed when the composite conductor is under uniaxial tension, which is the result of difference in elastic modules and yield stress between the axial substrate and the electroplated CU stabilizer. In this presentation, the stress-strain relationship of free standing CU stabilizer and a bare RABCO wire, that is a tape without any stabilization, was measured. The results are utilized for the calculation of stress-strain relationship of electroplated U copper stabilized wire using a two-component composite model. Given the thickness of the substrate and stabilizer, the calculated results agree well with the measured stress strain curves, which can be well fitted with the Ramberg-Osgood equation. The tensile strain and stress dependence of the critical current IC was measured at 77 Kelvin in liquid nitrogen. Depending on whether the critical current was measured with the wire under stress or after unloading, a critical strain or stress and an irreversible strain or stress were determined respectively. Now let us discuss further in this presentation. Introduction. RIPCO, where RE describes about the rare earth based second generation 2G high temperature superconductor HTS wires are now being made and supplied by a number of manufacturers for the development of various electric and electromagnetic devices include magnetic, SFCL, SMES cables and etc. The mechanical electromechanical properties are one of the most important attributes of 2G wire. Among these properties, the MIM behavior of a wire when it is under uniaxial tension has attracted more investigation. Although there have been many reports and publications, this aspect of the properties continues to be a focus of studies as the wire manufacturing technology is still evolving and the effects for practical application growing. A 2G HTS wire has typically a multi-layer architecture consists of a substrate, a stack of buffer layers, a REBCO layer and a stabilizing layers. In a coated conductors, the substrate and the stabilizer are the thickest layers, much thicker than the other functional layers. For this reason, the MIM properties of 2G wire under tension are greatly dependent on the properties of substrate and stabilizer. The substrate is the base of the epitaxial template and mechanically the backbone of a 2G wire. Depending on the wire fabrication technology, various substrate materials are utilized by different manufacturers. Typical substrate materials included astral, NiW alloys and stainless steel. The mechanical properties of the material are quite different for each other. The stabilizing layer typically made of pure copper, a copper alloy or stainless steel are realized by different techniques including coating by electroplating or lamination by soldering. In addition to providing the protection for a wire, In transition for the superconducting state to normal state, the stabilizer establishing layers also plays a role in mechanical reinforcing a 2G conductors. These studies on the properties of 2G wires under tension has been focused mostly on the effects of strain stress on critical current. A practically very important result is the determination of strain stress limits below which there is no or negligible degradation in IC. To define a critical stress at which the IC drops it to a fraction of its original value, this critical strain here in offset can be readily determined for a normalized electrical current versus stress and relationship measurement. On the other hand, there exists an irreversible stress strain which is characteristic limit that manifests whether there is any permanent or unrecoverable damage to conductors or whether the IC can return to its original value after unloading. The studies on the stress and strain limits of 2G HTS wire under the tension has confirmed that the most prominent effects are from the substrate. In this presentation, we study on the stress strain relationship of 2G HTS wire made a astole substrate and the electroplated Q stabilizer. The uniaxial tensile strength tests were carried out at the 77 Kelvin, not only on Q stabilized fully processed wire but also on bare ripcord tapes, no stabilization. For the first time, we also conducted a 77K uniaxial tensile stress test and freestanding electroplated copper stabilizer sample that were prepared from a fully processed 2G wire. Following the result on the stress strain relationship, the stress and strain tolerance of the wire is also reported. Introduction: the Ripco wire were made by superpower industries using a IBAD magnesium oxygen MOCVD technology, and it was deposited on a electropolished astral substance that was 50 μm thick. In the buffer tank, the cap layer was LaMnO3. The Ripco layer was deposited using MOCVD. Now let us observe the figure in which it describes the experimental setup for the stress relationship testing and IC measurement under uniaxial tension at 77 K in liquid nitrogen. In the image, it is shown the setup in the stress relationship testing mode. A 1.5 thick AG layer was then deposited on the Ripco as a contact and a protection layer by magnetron splitting. The CU stabilizing layer was deposited by a conventional electroplating process using a sulfuric acid based bath. All the processes were operated in a reel-to-reel mode. A uniaxial tensile stress were carried out on a universal tester. A customized setup was built to have the sample wire to be tested when immersed in liquid nitrogen. Shown in figure is a setup used for both stress relationship testing and the IC measurement under tension. In the cooling down of the sample from room temperature to 77 K, a force free mode was activated in the tester such that its crossheader moved automatically as a response to a thermal construction of the mounted sample. In the way, there was almost no thermal stress generated in the sample throughout the cooling down process before any measurement started. A load cell was used to measure the forces. A nailless type double extensometer, the gauge length of which was 50 mm, was mounted on the sample wire to measure its elongation strain. The total length of a tensile test sample was about 220 mm. In measuring the stress strain relationship of fully processed and bare Ripco wire, 12 mm width sample were used. The width of a free standing electroplated CU stabilizer sample was 10 mm. The CU sample was prepared by peeling off the HTS side CU stabilizer from an original 12 mm wide fully processed wire on which 1 mm width material was sheared off from each edge before the peeling. For the stress strain relationship measurement of all the sample, the stress rate was about 2.4 into 10 to the power of minus 5. In measuring the stress strain, the IC under tension measurement was carried out using the 4 probe method. The CU grips at the end of the sample wire were also used as electrodes to apply the current. The DC current was applied with a ramp rate of about 200 amps per minute. The voltage tab spacing was 70 mm and the voltage tabs were mounted on the wire by clipping. The distance between the CU grips was 120 mm. For measuring IC of a fully processed wire, a 12 mm white tape was used and the IC retention was 1 mu V per centimeter. For measuring the IC of bare Ripco tape, in order to carry out repeated IC measurements on one tape and avoid possible burnout, a bridge of about 2 mm wide was made by chemical etching and the IC certification was 0.1 mu V per centimeter. The IC of 2G HTS wires studied in this work were in between 360 to 460 amperes per centimeter of weight. Results as stress strain relationship. The figure 2 discusses about the stress strain curves of a bare Repco tape and the freestanding electroplated CU stabilizer. And the figure 3 describes about the calculated and the measure of stress strain curve at 77 Kelvin for 2G HTS wire. And the figure 4 describes about the fitting of the measured stress strain curve of different wires using the Ramberg-Osgood equation. And the table 1 describes about the 77 Kelvin stress strain curve fitting parameters for different tapes. And the figure 5 describes about the tensile stress and strain dependence of the normalized critical current. Conclusion. Tensile tests were performed on the freestanding electroplated CU stabilizer, resulting in elastic and inelastic modulo C of about 70 gigapascals and 85 gigapascals and yield stress of 0.2 of about 200 megapascals and 400 megapascals at RT and 77 Kelvin respectively. Based on the measured stress strain relationship of copper stabilizer and the bare Ripco tape, the stress strain relationship of any copper plated wire can be calculated using a two-component composite model with an equal strain assumption. It is shown that the measured stress strain curves of different wires can be well fitted with the Ramberg-Osgood equation. The experiment measurements result suggestions that the elastic module yield stress, critical stress and irreversible stress of the Ripco wire decreased with increased CU thickness or CU thickness ratio. Critical strain and irreversible strain were independent of CU thickness, being intrinsic values of 0.45% and 0.75% respectively. Thank you.